Clay soil is one of the most stubborn textures a gardener can face. It compacts tightly, resists water penetration, and suffocates roots by limiting oxygen flow. When dry, it hardens into near concrete. When wet, it becomes sticky and unworkable. Yet clay has a hidden advantage. It's nutrient-dense. The problem isn't fertility but structure. To unlock that fertility, the soil must be restructured into a looser, crumbly state where microbes and roots can thrive. This is where worm castings enter the picture. Gardeners have long known that worm castings are rich in microbial life, humic substances, and plant-available nutrients. But the question that sparked our test was not if worm castings work, it was how long it takes for them to noticeably transform clay soil. We ran a staged trial to measure the changes step by step. Before introducing worm castings, the clay was measured for baseline conditions. A soil test confirmed high levels of potassium and certain micronutrients, but compaction was extreme. The infiltration rate of water was almost zero. A hose running on low for 5 minutes barely penetrated the surface, pooling on top instead of soaking in. When pressed, the soil broke apart into hard clods rather than loose crumbs. At this stage, roots would have struggled to spread, and microbial activity was minimal. Clay this dense effectively shuts out oxygen, creating an environment where beneficial soil organisms cannot function properly. Worm castings were applied at a rate of about ½ an inch across the bed, then lightly mixed into the top 3 inches of clay soil. The idea was not to till deeply, but to introduce biology where it could begin colonizing. Worm castings carry an extraordinary range of microbes, bacteria, fungi, actinomycetes, that immediately begin feeding on clay's bound particles and releasing nutrients. In addition, worm castings add humic and fulvic acids which act as natural chelators. These substances help break apart mineral bonds in clay, creating tiny pathways for water and air. This is really the foundation of structural change. Within the first week, small but important changes were visible. After a light watering, the soil surface no longer pooled water in the same way. Instead, droplets began to penetrate more evenly, though still slowly. Microbial respiration was at work, generating carbon dioxide and loosening soil particles on a microscopic level. By the end of 2 weeks, a shovel could more easily break into the soil. Though clods were still firm, they fractured with less effort. The smell of the soil shifted too. It no longer carried the sour, anaerobic scent of stagnant clay, but began to take on the earthy aroma gardeners associate with living ground. This was an early sign that microbial life from the castings was establishing itself. After 4 weeks, a significant structural difference was measurable. Infiltration tests showed that water applied at the surface soaked in at more than double the baseline rate. Soil that once compacted into bricks now showed the beginnings of aggregation. Small, crumbly clusters that held together when pressed but allowed air spaces between them. The real proof came from earthworm activity. Although no worms had been intentionally introduced, their castings and tunnels were visible. This indicated that worms were migrating toward the improved soil, drawn by microbial signals and organic matter. Worm castings not only brought microbes, they created conditions that invited earthworms to colonize and continue the transformation naturally. So between 60 and 90 days, clay soil treated with worm castings underwent its most dramatic change. Roots from test crops, like radishes and beans, spread through the soil without being stunted or forced sideways. The presence of mycorrhizal fungal threads was actually visible under a microscope, forming networks that further aggregated clay particles. By this point, the soil no longer behaved like pure clay. When wet, it held moisture without suffocating roots. When dry, it did not harden into impenetrable chunks but retained enough structure to stay workable. It had transitioned from hostile ground into a biologically active, friable medium. At the 6-month mark, the soil had effectively stabilized into a new state. Humus content had risen, and you could actually see this by the darker, richer color. Microbial respiration rates, measured with a simple carbon dioxide burst test, were 3 times higher than the baseline. Most importantly, this transformation proved to be durable. Even without further additions of worm castings, the structure remained loose, thanks to the continued work of microbes and worms now living permanently in the soil. So a natural question arises here. Why did worm castings accomplish this transformation so quickly, while compost or mulch might take years in clay? Well, the difference lies in biological concentration. Compost does contain microbes, but worm castings are, honestly, like a microbial superfood. Every particle of casting is coated with colonies of bacteria and fungi that are already adapted to break down organic matter. Additionally, worm castings include polysaccharides and humic compounds that actually glue clay particles into aggregates. This is a direct structural fix, not just a nutritional one. Compost provides food for microbes, but worm castings provide both food and a living inoculant. And that, folks, is why clay responds so rapidly. For gardeners dealing with clay, worm castings should be viewed more as a microbial starter rather than just bulk organic matter. Applying a half-inch layer across a bed is usually enough to jumpstart change, especially if you follow up by mulching with leaves or straw to keep conditions moist. Mixing deeply really isn't required. In fact, shallow incorporation works better, since most microbial action begins right at the topsoil. So, the real key here is patience during the first month. Results might seem pretty subtle at first, but once those microbial colonies start to establish and worm migration gets going, the pace really picks up. By about 3 months, most gardeners will notice roots exploring places they just never could before. And by 6 months, honestly, the clay has been effectively transformed into a living, humus-building soil. The lasting benefit of worm castings in clay isn't just about immediate structure, it's really all about humus formation. Clay soil, once it's broken down by microbes and stabilized with organic compounds, actually becomes one of the most fertile soils you can have. Unlike sandy soil, clay holds nutrients tightly once it's properly aggregated. The addition of worm castings shifts clay from being a barrier into being a resource, with long-term fertility built right into its very particles. Our test showed that worm castings can turn lifeless clay into thriving soil in as little as 3 months, with full structural change by 6 months. For gardeners struggling with compacted ground, this is honestly one of the fastest and most reliable methods out there. The transformation isn't magic, it's microbial science in action, concentrated and accelerated by the unique biology of worm castings. If you're ready to unlock the fertility hidden in your clay soil, start small but, be consistent. Worm castings don't just feed plants, they actually reprogram the soil itself, making it hospitable for life from microbes all the way to earthworms. The results really do speak for themselves, and once established, the benefits last for years. To keep learning practical soil revival methods that are tested and explained in depth, make sure to subscribe to Hydro Haven and share this guide with other gardeners. Your soil has hidden potential. Sometimes it just needs a little help from worms to show it.